All right, so today we're going to talk about section 3.5, which is all about solving equations using exponential and logarithmic functions. So that include them or using those. So recall that we have this equivalence with exponents, and we learned this back a section ago. And if we have b to the x and b to the y, given that b has certain conditions, right, it has to be greater than 0 and not equal to 1, then we can just automatically imply that x equals y. So we can set the exponents equal to each other. Another thing we're going to want to remember is certain laws of exponents. So given a and b being some real numbers, either positive or negative, does not matter, we have these certain rules. So you can move them back and forth. So if you multiply two things together with the same base, right, the base is this, if you add their exponents, right? So x squared times x to the third equals x to the fifth, right? We add their exponents. If you have two numbers or two things that have exponents divided by each other, you subtract their exponents, right? X to the third over x squared. That's going to give me just x to the first, 3 minus 2. X to the negative a is going to cross the fractional bar to become a positive 1 over x to the a. So this is just an important rule to memorize. And then if you are raising some power to a power, we multiply those together. This is the most important rule that you need to remember for this section. So let's solve this equation here. So we have 3 to the x equals 9. Now remember, we were doing this beforehand where we were taking 9 and we're writing it in terms of this base here, 3 to the x. So we're going to write this as 3 to the second power, right? So this implies x equals 2. So that's how we're going to want to do this. Whenever we have an exponential equation, we always rewrite it in terms of the base that we have. Okay, so let's try this one. So we have 64. So we have 4 to the 2x minus 3 power, and this equals 64. So we need to figure out what 64 is in terms of 4. So we have 4 squared is 16. 4 to the third is going to give me 64. So we have 4 to the 2x minus 3 equals 4 to the third. Then if I set this equal to each other, I have 2x minus 3 equals 3. Okay, so I have 2x minus 3 equals 3. Add 3 on both sides, add 3, so I get 2x equals 6. Divide by 2, x equals 3. Perfect. And so we can check this to make sure. So we get 4, 2 times 3 minus 3, which gives me 4 to the 6 minus 3, which gives me 4 to the 3. Okay. When we have variables in both exponents, we do have to be careful. So for these ones, we just had a number, and then we had like an exponent that was a variable. But let's just practice rewriting this in terms of base 5. So this is going to be 5 squared, right? That 25, all raised to the 4 minus t. Now, remember, the rule is x to the a times x to the b, or nope, not this one. X to the a risen to the b power is xab. Now, you have to be very careful. Since this is a 2 here, and this is a expression, we need to write this as 5 to the 2 times 4 minus t. That's how we write this, and then we would distribute, so I get 5 to the 8 minus 2t. You have to be super careful. If you just distribute the 2 onto the 4, you will get this problem wrong. So be very, very careful when you are rewriting things like that. All right, let's try this one. So both bases are probably going to have to be rewritten. So let's practice and focus on this 27 first. So 27 is 3 to the third power. So I'm going to write that as that, 2w plus 5. Now you may be thinking, how do we know to convert it to 3? Well, most of the time you're going to want to boil it down to the smallest amount you can. right? So since we have 3, right, 3 is a prime number, so that's usually what you want to boil the base down to. Now with this last problem, right, we had 4, but since 64 can be written in terms of 4, we could just do it that way, since this one's already there. We could have, though, rewritten this as 2 to the 2 times 2x minus 3 power equals 2 to the 6 power. We could have written it like that and we would have gotten the same answer. But sometimes it's easier if it's like 2's and 4's to leave it the way that it comes in the exponent, if you can do that. Okay, now we rewrote this side, the 27 side. Now let's rewrite the 1/3. Now 1/3 is 3 to the negative 1 power, right? So I'm going to write this as 3 to the negative 1 all to the 2 minus 5w. So we had to rewrite both bases in terms of powers of 3, right? That's what we did. Now we can get rid of those exponents. So we get 3 to the 3 times 2w plus 5. So I want to combine my exponents, is 3 to the negative 2 minus 5w. You have to be very careful here as well, right? We're distributing that negative 1. So I get 3. So now that I have my bases the same, we don't even have to do any more work. We have 3 times 2w plus 5 equals negative 2 minus 5w. Now I solve this equation. So I get 6w plus 15 equals negative 2 plus 5w. Now I can start to solve. Minus 5w, minus 5w, minus 15, minus 15. W equals negative 17. Okay, so I get W equals negative 17, and we can check that. It will work, and that's going to be the answer. So again, you have to be really careful, and these are tedious, and it's easy to make a mistake. Okay, let's solve this one. 5 to the x power equals 15. All right, well, we need to write this in terms of 5 to the x equals some base here to some exponent that equals 15. Now, can you think of a way to break down 15 into powers of 5? Well, we know 5 to the first power equals 5. 5 squared equals 25. 5 cubed equals 125. Unfortunately, 15 is not in that mix. So at the moment, we don't really know how to solve this. So when we have an unrecognizable power, we're going to have to use the inverse of exponentials to get that x down and by itself. So recall this property of logs where you have the base the same as the base of the log, the same as the base of the exponents, and you just get the exponent back. So let's go back to this 5x equals 15. And in order to get x equaling something, I need to take the log of both sides. Now, there's a couple different ways to do this. I'm going to do it with any base. So I'm going to pick base 10. Okay, I'm going to use base 10. So if I want to get the exponent down, remember our properties, our power property, log of b to the x equals x log b. So I'm going to take log base 10 of both sides. Remember, whatever you do to one side, you have to do to the other. And it's completely fine if you're solving an equation and you want to use logs to solve it, you just have to do it to both sides. So log base 10, so I'm not going to write it, 5x equals log of 15. Remember that property where if you have log of b equal or log of x equals log of y, then y equals x. This is the same idea, same property, we're just going in reverse. Now I'm going to bring that x down, log 5 equals log 15. By power property of logs, now I'm going to divide by log 5 on both sides, divide by log 5 on both sides. So I get x equals log 15 over log 5. This is going to be the answer. You're no longer going to have pure number answers. You're going to have these logs, and it's going to be some type of a decimal approximation. So that's why when you don't have pure terms of some exponential, they are going to become decimals and fractions. Okay, so that's the first way you can do it with log base 10. Pretty easy enough. But you can do it with the base that you're given. So if we have 5x to the 15, another thing that I could do is instead of taking log base 10, I could take log base 5, because remember that property here, if I have base 5 here and 5 here, they're going to cancel and I'm just left with x. So if I take log base 5 of 5x equals log base 5 of 15, This all cancels, and I'm left with x equals log base 5 of 15. Now this is faster, and you might be saying to yourself, well, why on earth does this, why is this different than this answer over here? Aren't they supposed to be the same thing? They're the same equation. The answer is, algebraically, they are equivalent. Numerically, they are equivalent. This answer uses the change of base formula to achieve that answer. So you use change of base here to get to this answer over there. Remember, you take log base 10, so log 5/15 equals log base 10 of 15 over log base 10 of 5. Again, that's what we're doing. That's technically why it doesn't matter which way you do it. Either answer is acceptable. Okay, so let's try another one. Let's try this answer. So we have 4 to the 2x minus 7 equals 5 to the 3x plus 1. Now the exponents are, so both of these bases are different. We cannot break them down. So we can have a choice to do this either way we want to. I'm going to use just log base 10. So I'm going to use base 10. Again, it doesn't matter which one you use. You're going to get the same answer in the end. Okay, so if I use base 10, I'm going to get log of 4 to x minus 7 equals log 5 3x plus 1. Then I'm going to bring these exponents down, so I get 2x minus 7 times log 4 equals log 5. Oh, let's bring down this 3x plus 1 times log 5. Now that we have brought those powers down, we need to distribute through to the logs. So we get 2x log 4 minus 7 log 4 equals 3x log 5 plus log 5. Now I'm going to move the x's on one side and the pure logs on the other side. So we have 2x log 4. I'm going to subtract this minus 3x log 5 equals, I'm going to add this 7 log 4 plus log 5. So I've gotten pure logs on this side, which if you were to punch in your calculator, you will get some type of number. And then I've got the x's over here. I'm going to factor an x out, so I get 2 log 4 minus 3 log 5 equals 7 log 4 plus log 5. Now I'm going to divide by 2 log 4 minus 3 log 5 on both sides. 2 log 4 minus 3 log 5. And I'm left with x equals 7 log 4 plus log 5 all over 2 log 4 minus 3 log 5. And so you are left with this mess of logs, but if you were to type this into your calculator, it's approximately negative 5.5034. So this is what it approximates, but again, you could just leave it like this. Okay, let's solve this exponential equation. So we have exponents on one side and a number on the other side, but we have addition there. So the question is, how are we going to solve this? Okay, so this is not going to work out the way that we have it over here with the other ones. We're not going to be able to just like take logs or whatever of both sides. It's just not going to work. So we're going to do a little U substitution method. So let's do a U substitution. Sometimes in mathematics, U substitutions are a very popular thing to use when you have difficult equations that can't figure out how to solve. So I'm going to let U equal e to the x. U squared is going to be e to the 2x. Okay, so this is going to be my box here of my U substitution. Now I'm going to plug these into my original equation. When I get my answers at the end, I'm going to have to go back because I'm starting in terms of x. I'm doing some algebra manipulation to turn it into U, but at the end I'm asking for x back. So I do have to be very, very careful here. Okay, so I'm going to get U squared plus 5U minus 36 equals 0. This is a quadratic equation we know how to solve. So let's solve this and figure out what this will be. So I can factor this as u minus 4 times u plus 9 equals 0. Now I can set each factor equal to 0 and solve. So I get u equals 4, u equals negative 9. Now go back to my box here, my u substitution box, and I look to see, okay, u was e to the x, so I get e to the x equals 4, and I get e to the x equals negative 9. So now I look to see, okay, is this one possible? Can e to the x ever be negative 9? No, because exponentials can never be negative. Exponentials answers are negative, never negative. So exponents, solutions are never negative. When you're asking like this and solving it like that, you can never set it equal to a negative. Now this one is fine though. Let's take the natural log of both sides. So we get x equals ln of 4. That's going to be my solution, which is 1.3864363 approximately. Okay, so now let's talk about log equations. So if we have some log base b of x equaling log base b of y, then we set their arguments equal to each other and solve. This would be the same thing as writing it in exponential form, right? It's the same kind of idea. Now we just have logs. So let's solve this first one. We have log base 2 of 3x minus 4 equals log base 2 of x plus 2. They're the same bases, so we can set those arguments equal to each other. X minus 4 equals x plus 2. And solve. Minus x, I get 2x equals, add 4, 6x equals 3. Simple enough. And then you might want to check your solutions just to make sure, but this is going to work. Okay, so that's the first one. Let's try this one. So now we have 3 logs. Now we actually have to be careful because we only have the formula for logs on both sides, and also don't get caught up with natural logs. Remember, they're the same thing as ln equals log base e, so don't get hung up on that. So I'm going to use my properties of logs to kind of rewrite this. So ln x minus 4 equals ln of, this is x plus 6 over x, right? If you're subtracting, it's dividing. Now I have logs on both sides. I can take x minus 4 equals x plus 6 over x. Let's multiply by x on both sides to get that out of the denominator. So I get x squared minus 4 equals x plus 6. Let's move everything to one side. So that's x squared minus x plus 2 equals 0. And now what I'm going to, we missed an x here, minus 4x equals x plus 6, okay? Now I have x squared minus 4x minus 5x plus 6 equals 0, minus 6. Now I can factor this as x minus 6, x plus 1 equals 0. Set this equal to 0, so I get x equals 6 or x equals negative 1. Let's just make sure that this works. If I plug 6 into every single one, I'm going to have 6 minus 4, which is positive 2. That's going to be fine. 6, that's 12. 6, fine. If I plug negative 1 in, though, it's going to be ln of negative 1. This is undefined. So this one, not a solution. This is the only solution. So you always want to check your answers when you're solving logarithm equations because you never know. All right, let's solve this one. So we have 8 log base 4 w plus 6 equals 24. First step, let's get the log by itself, divide by 8. So now I get log base 4 of w plus 6 equals 3. Now, since I have a log on one side and a number on the other side, what I'm going to do is I'm going to rewrite this in exponential form to solve for w. So 4 to the third power equals this. So I get 4 to the third equals w plus 6. Now 4 to the third is going to be a big number. That was 64 equals w plus 6. I'm going to subtract 6 on both sides, minus 6. W equals 58. And if I plug this in, this will work. That will work. So always check your solutions. All right, let's try this one. So we have log base 2 of x equals 3 minus log base 2 of x minus 2. I want to get logs on one side, numbers on the other side. So let's add log base 2 of x minus 2 on both sides. So that's log 2x plus log 2 of x plus 2, or x minus 2, equals 3. Remember, if we're adding, we're multiplying logs, so let's condense those together. X squared minus 2x equals 3. So I'm just multiplying that x and x minus 2. Now let's rewrite it in exponential form. So I get x squared minus 2x equals 2 to the third. So I get x squared minus 2x equals 8. Minus the 8 over, I get x squared minus 2x minus 8 equals 0. Factor this as x minus 4, x plus 2 equals 0. So x equals negative 4, x equals 4, and x equals negative 2. Let's check. Since we're starting off with log of just a number of just x here, automatically this one's disqualified because you cannot have a log of a negative. So x plus, or plugging in x equaling 4, that's 4, that's good. 4 minus 2 is positive 2, check. So this one is going to be our solution. Okay, let's solve this last problem. If we have two logs like this, we have log base 10 of x squared plus 7x equals log base 10 of 18. Both the logs are the same, so we set the argument equals to each other. So we have 7x plus 18, or equals 18. So that's x squared plus 7x minus 18 equals 0. Factor this, so I get x minus 2, x plus 9 equals 0, x equals 2, x equals negative 9. Since we have this log and we need to test both solutions, so we just need to check if x squared plus 7x is greater than 0 for x equaling 2. So that's 4 plus 7 times 2 is greater than 0. Check. And plugging in negative 9 gives me 81 minus 63, which is greater than 0. So both of these solutions are going to work. So for both of those will be the solution. So solution set, x equals negative 9 and 2. And that's going to be how we solve log and exponential equations. And we use those for applications. You can review Blackboard and the textbook for the applications.